Sorry about that. I don't know. It all played fine on my computer, so I don't know what the deal is. But it just didn't find when I uploaded it, or it didn't play when I uploaded it. Um, okay, can you all see my screen?
Yes.
Yep.
Great. All right. Let's go over the agenda for today. And by the way, happy St. Patrick's Day. Um, so the agenda for today is I'd like to spend a little bit of time on reviewing Q&A. Any sort of questions that you have about the homework, about regression, or whatever. I would also like to do one example, one kind of final follow-up of an example from regression, just to kind of get us on the same page. And at that point, I want to cover design of experiments. And in particular, what we are going to cover is what a statistician calls 2 to the k design of experiments. Now, in its simplest form, this is known as A/B testing. And that's an invented word that just came up recently. Statisticians didn't used to talk about that, but in its simplest form, that's what's called A/B testing. I have one thing, I'm testing one condition, A versus B. So we'll talk about DOE. We'll give some sort of justification first and setting. And what are some advantages and so forth. Then I want to give an example, and then we'll talk through the terminology. We'll do what's called a full factorial experiment, and then we'll do a fractional factorial experiment, and then we'll recap. Now, what's interesting about design of experiments is that every little piece of it is easy, but there's a lot of little pieces. There's a lot of little pieces of it. So it may behoove you to, as we finish, to review one thing or another, either in this lecture or some of the other recorded lectures, so that we get the examples right. We will today not be using Excel stats after we finish the regression. We'll be using something called DOE Helper, which everybody should have. It's in your tools directory. So it's called DOE Helper. It's an Excel file that we'll use. All right, so any questions before we get going? I should say, what questions do you have on anything? We'll start the first part of the agenda. What questions do you have sort of outstanding from the other lectures or from the homework or anything like that?
Mark, this is Regina. Our prior assignment, when will those be available to us?
I will be getting those back as soon as possible, so either this Friday or prior to this Friday.
Okay. I'm just trying to take a look to see if I think I had a question on multiple regression exercise 3 production costs, but I can't recall what it was right now. Sorry.
No, that's okay.
If I can locate it.
Okay. Can you tell me what page it was on in the book?
Let me take a look.
Sure.
It was on 100, week 5, 100.
Mm-hmm. Okay. Let's take a look at it. So, production. All right. So this is production cost.
Yeah.
Okay.
I think this is the one where maybe it wasn't this one. I'm sorry.
That's okay.
I know there was one of the homework assignments, and maybe I'll chat with you after class, where it was the fan shape, and I was having trouble with the Excel stats when I completed the picture. Maybe it was Forbes.
Oh, the Forbes one. Okay, right.
Yeah, sorry, it was Forbes, slide 134.
Okay. Okay, so let's go over that one together because I think we didn't really cover that much in class. So I wanted to make sure that we do. I know that there's a full video on it, but let's go over this one in class. So let's open up Forbes. So this is data that's taken from many other I think It's fairly old. It's 1986, but it's taken from many industries, and there were originally many variables in this data set, maybe 20 or 30. And the idea here, I think, was to say, how would we make some valuation of a company? And so one of the things to see would be, how are things correlated in this company? Like, for example, assets to sales. Are assets correlated with sales in a company? And so we've got, just kind of going back through our data analysis algorithm. Whoops, hello, there we go. Oh yeah, white on white is not so good. All right, so here, I think what we're looking at is, can we predict assets from sales? That's just the question that we're asking. And this is a number, and this is a number, so it's natural to start with a scatter plot. Whoops, hello, scatter plot. Okay, so let's go ahead and do that first before we do anything else. So going in Excel stats, got to open it up first. Going in Excel stats, we go to ToNum, and let's just take a look at that. All right, so what's kind of different about this, and you should see this immediately, is that we've got, let me see if I can zoom in a little bit more. There we go. There we go. Okay. So you've got a number of really influential points. And so, for example, we've got this point way out there, and it might make us think that, you know, a line that fits that is a pretty good line. But look at all that scatter. Huge amount, right? Worse than that, it's really bunched in closely to here. So it's got a small amount of variation here, but it's got a huge amount of variation here. And one last thing to kind of note is, if we took this point out, would we really even draw this line at all? Maybe we draw a different line. Maybe if we took that point out, we might draw, you know, a totally different line. Maybe we would draw, and I'm just making this up, but maybe we would draw this line instead. So that point can have a tremendous amount of influence, and we don't want to always have that. Well, one way around that, and I think to your point, Regina, is that if you went ahead and did do the regression just as is, and you got to this point and you did the residuals, you get the dreaded fan-shaped residuals. Where are they? Right here. Right now, we knew we were going to get that because we could see it from the plot. So how do you deal with something like that? Well, one way of dealing with that is to change the scale of the measurement. That's not what I wanted to do. I wanted to go back. I'll just close that up. Okay. One way is to change the scale of the measurement, and that's called a transformation. So if we transform a one or both of these things, what we're essentially doing is we're smushing in the scale, or we're changing the scale. Let me show you what that does, and I'm going to use a different program than we have here. No worries, because we'll use Excel stats to do this in the end. But I wanted to show you using a program that I think shows you more vividly what a transformation really does. It's this fellow right here, Data Desk. And
that's what was in the video, right, Mark?
Data Desk might have been in the video, yes.
Yeah, I think that's why I got a little lost.
Okay, all right. So this is just kind of showing you what a transformation does. So a transformation changes the scale, and let me just make a plot of this as a histogram, and we'll just do sales, okay? And so what I'm going to do is I'm going to let's see, transform, and I'm going to do something called a box Cox transformation. Now, you don't need to know what that is exactly to know that what I'm doing is I'm changing the scale. I'm going to change this X scale so that a large number is not as relatively large. And that's what happens. Let me plot this. That's what happens when we do that. So when you make a transformation, this is the original variable right now. Looks exactly like it did to start. And then as we do different transformations, like I'm going to move to a square root. Watch what happens as I do this. This is a square root transformation right here, but can you see it became less skewed? In other words, some of these really giant ones became now visible to me, and so forth. And I can make this happens to be a log transformation right here. Definitely looks more regular, right? There's some small values, there's some big values, but it's almost like all the values are on an even playing field. So that's what a transformation does, is it changes the scale. Okay? So that's what a transformation does. Now the most common transformation, and a transformation changes the scale. Why do we care about that? Well, it's because we can get a hand. It makes it easier for us to see things in a plot, and it very often makes it easier to interpret things. So let me give you an example of what a transformation is doing. We're going to use the most common one is a log transformation. And it's just got a lot of nice little mathematical properties along the way, as well as being kind of useful, helpful. So a log transformation does the following. If I have x, whatever my variable is, let's say my variable is 1,000 or 100,000 or 10, what the log of x does is it says this x is equal to 10 to the what power. So for example, the log of x, if x were 1,000, the log of x is 3. Hopefully that makes some sense. If my number is 100,000, the log of x is 5. It's how many zeros, right? If x is 10, the log of x is 1. If x is 0.1, which is equal to 1 divided by 10, the log of x is minus 1, and so forth. Okay, so it's you might recognize this as scientific notation. So that's essentially what the log of x is doing. It's squishing down big numbers into much smaller numbers. Now, one last thing. The log of 100 is 2. The log of 1,000 is 3. What's the log of 500? Well, I don't know the answer to that, but it's somewhere between 2 and 3. It might be 2.7. I just made that up. I don't know what it is exactly, but I know it's somewhere between 2 and 3 because that number 500 is between 1,000 and 100. Okay, so that's what that is. Incidentally, and you may find this kind of interesting, so I don't know, maybe not. A million, which the log of that is 6, right? There's the log of x, if this is x. A million, the log of that is 6. A billion, the log of that is this. It's 10 to the 9th. There's a number for one with 100 zeros on it, and I won't draw it. The log of that is 100. It's called a googol. That number is called a googol. And it's spelled differently than the company, but I'm not totally sure that that's where the company got their name, but I think it is. I'm pretty sure it is where the company got their name. They called their name Google because it's one of the invented numbers that's really big, a googol. All right. So back to the regularly scheduled program. This is what one of the most common transformation is, and you can see how it shrinks in, makes big numbers small, and makes very small numbers like 1/1,000th. It makes it a little bit easier to read. All right. So let's see. So now let's do this in Excel stats, and let's take a look at some of these transformations. So if we take a look at the transformation of assets, you can see the original. This is the original. It says it right on the bottom here, original. Let's take a look at the log. Yeah, the log looks much more regular. In fact, it looks kind of bell-shaped, doesn't it? And here's the square root. So it looks basically exactly like it did in the data desk example that I just gave. Then there's another one that we pretty much never use, arcsign. All right, so we might try taking logs of this data and see if that helps us. So let's try doing that in Excel. So to do that, we'll just call this the log of assets and the log of sales. And now we have to calculate it. It's equal to log of assets. And this is equal to log of sales. All right, and let's just see if that works. It looks like it makes some sense. Geez, I have so many decimal points. I don't need that many. I don't want that many, in fact. Get rid of some of them. Okay, there we go. So let's see if this makes sense. So the log of 1,000 is 3. The log of 10,000 would be 4. This is between 1,000 and 10,000. Makes sense. The log of this one should be bigger than 5. Bigger than 4 because it's bigger than 10,000, but smaller than 5. Let's see if that's true. Yep, it is. So it looks like this is working properly. It looks like that's making some sense. All right. So let's go ahead and now I'm going to do the regression of this. And we'll take a look at it and we'll see how much different it really is. So there it is. I just replaced that data with that. And you can see already that the regression is much more regular. If I show that line, now it's an interesting line. It's funny that it's not where I expected it to be. If you were looking at this, and before I drew that line, my guess was that it was going to. My guess was that it was going to be like that, but it wasn't. In any event, it helps us see a lot of other things that we maybe didn't see before. Like, for example, when you look at many other of the variables, there's a number of different outliers or patterns that become apparent. Are there any outliers or patterns that you see in this particular scatter plot?
So it looks like there's lines, maybe at what point is that? Just past starting at about 3.5.
Yeah, see if I can get, yeah. So it looks sort of like, to me, I agree. So it looks like there's a couple of different things that are going on here. Like, for example, this, right? Maybe there's a couple of parallel lines going on here. Now, it's not that evident, but if you look at it, these are companies whose assets are relatively high compared to their sales. And when you look at many other variables that were in here, this is just one example, but these turned out to be all savings and loans. And if you remember what was in 1986, many of us do not, but there was that big crash, the savings and loan junk bond stuff that happened in 1986. You could see it in the data. You could see the companies that were overvalued. The only way you could see it, though, is if you kind of took out your microscope, and taking a log of something is kind of like that. So that's technically how you do it. You just take the log and then you look at those variables instead of looking at the original variables. Do the regression on that. The main thing is to say, recognize when you want to do it. And that's not always that easy. There's a lot of art to it, and this is definitely one of the more difficult things for sure. Why would I want to do this as opposed to using the original variables, which I should have put into my regression. I should have put those in. Why would I want to use that instead of these? Well, when I looked at the residuals, I can see that there's a lot of variation here. There's some really extreme points, and I'm not that comfortable using that original stuff. So anyway, if you hopefully that helped a little bit. But you'd start with doing the regression on I think it was log of assets versus log of sales. You could get your regression line, and you'll see that when you do the residuals analysis now, it's much more regular. So it's a much safer regression to use. You see that there's no real pattern there, except for maybe this, and you might want to flag that. Okay, hopefully that helped a little bit. I'm not getting any response.
It did.
Okay.
It did. The data desk, I think, is where you showed that last scatter plot, how the data looked. And so when I ran it, I got the same thing you got today, and I just didn't know if, was that right? So it was more of a confidence
Okay, got it.
issue. Thank you.
All right, good. So it sounds like you did it right. Excellent.
Yes, thankfully.
Yeah, I think that, the hard part for most people is recognizing when or why I'd want to do this. Admittedly, there's some mechanics as well. So if you run into this as you're going through this and you find something where you say, oh, geez, I wonder if using a transformation might make sense. By the way, you can just pick up the phone at that point. But with me, I'm happy to talk with you about that. But you'll also usually see histograms that are extremely skewed. And that's exactly what you do see in this, right? The assets, very skewed. Sales, very skewed. But then when we take the log, they're not skewed. Log is the most common. Square root's the second most common. Those are the two that you usually try. Okay, great question. All right, well, I do want to do a quick recap of linear regression, and then I want to get right into a design of experiments. Now, let's see if I can. There we go. Okay. So we talked about linear regression, and the basics were with simple regression. It was, we looked at a num output, a response, or a y that was a num, and an x that was a num. Okay? And we learned that what we want to do is first look at the scatter plot. Here's our x, here's our y. Look for outliers, look for general trends, shape, and strength. Okay? If it looks like we might want to fit a line, then we do a simple regression, and that's just a y equals b0 plus b1x. And we're not done yet in terms of just plugging in. What we need to do is, again, remember that we look at the p-value first. P-values, so that's the fit. Second thing is we look at the r squared. That's the strength. And then we look at the residuals. Okay, and that just tells us sort of the robustness, just like in that last example. All right, and if all those are hunky-dory, then we're okay with making predictions with that model. What was the r squared that I said was really good? Rule of thumb? A good r squared is blank, around?
Above 70%.
There you go, 70 to 80. Now, in some cases, you might want it higher. In some cases, you might be willing to use something that's lower. All depends on how much you know about the problem. All right, and then there were some extensions. We said we could fit curves. Whoop, not curvers. We could fit curves if we did polynomial regression, right? So that helped us fit curves. So if we wanted to get an equation for something that looked like this, we could use polynomial regression. Okay? Then we also talked about just just now and a little bit briefly, we talked about transformations. That's one of the more difficult things, and it's also one of the, I won't say it's the least valued transformations, and that can help us with the robustness. Let's just put it that way. And by the way, transformations don't only occur within regression, they occur other places too. Sometimes when you're having trouble seeing something because data are too skewed, you might want to try a transformation. So you might want to try it with skewed data, even doing something else. Okay? That might be important to note down. And we also talked about dummy variables or indicator variables. And that was what happens if we have a y and we have an x that's a cat, right? Now we can have two different x's, but we have one that's a cat. This will help us with that sort of variable. And then finally, the most important one was we talked about multiple regression. And multiple regression is the most important because it can help us really improve that R squared, right? In other words, it can really help us get a much better R squared and make better, stronger predictions if we don't have enough to start with. Okay, so I want to go through one more example, and we've seen it before, but I think this will be a decent recap example, and that is, let me close everything down here. Okay, except for I'll leave Excel statistics up. And that is the January temperatures. Hopefully we've left all those behind. Okay, so with this one, I'm going to move this over for just a second. And for this one, I think we found that here we've got here we've got a y variable, January temp, and we've got an x variable lat, and we've got an x variable long, and then we've got another variable. And I wanted to just emphasize this because this may not be evident, but when we made our indicator variables for the forms and stuff like that, we didn't do what we did here. Here what we did was just to say, hey, it's West Coast or it's not West Coast, and we captured that all in one variable. What we did in the other indicator ones was we made it complete, and I'm going to do that right here. I think you'll get it in just a second. I'm going to call this not West Coast. It'll turn out that we don't need to do this, but I just wanted to show this for emphasis because on the other ones, when we did, remember that one with forms where we're looking for productivity, but we had the type of form as well, and we added that in, and we had 5 different types of forms, A, B, C, D, and E, and it turned out that we only needed switches for A, B, C, and D. We didn't need one for E, and this is kind of why. So if we were going to make up a not West Coast variable, it would basically just be the opposite of this one, right? It'd be a 1 where it's ever 0, and a 0 wherever it's 1. So for example, Los Angeles is West Coast, so the indicator for not West Coast would be turned off for that. Denver, for example, is not West Coast, so that would be that indicator variable. Hopefully that makes sense to everybody. I'm just going to do a quick check when I finish here. Oops. Okay, I think we got it all. And I'll do a quick check just to sum of these, and this is equal to sum of these two columns. It should all be 1. And let's see if it is. Yeah, I don't see any zeros. Okay, let me delete that. Okay, and now we'll add all these into the mix for multiple regression. Remember, for that we're picking n num. I want January temperature. I want to include the constant. I've got the lat lon. Let me take these out. Okay, so remember, if we only had one, we could look at the scatter plot between these. There it is between latitude and longitude. Looks pretty strong. There's our singular regression, 71% R squared. See if we can improve it with longitude. We look at our R squared again, did go up, or our adjusted R squared did go up. Longitude is significant, so we would keep it in the model. Now let's take a look at that West Coast versus non-West Coast. And remember, you would only see this by looking at the residuals, looking at the data, and stuff like that. So it's probably worth it to actually take a quick look at the residuals. Yeah, look at that. There's a couple that are really out there, like this one right there, maybe this one. When we took a look at the, hey, is it West Coast or not, I believe that some of that removed a little bit of that. So I'm just going to add that West Coast variable in there. Multiple regression went up quite a bit to 89% adjusted R squared. Let's take a look at that residuals. So yeah, that helped a lot. That helped a lot. Certainly looks more regular. There's still a couple of outliers, but not too bad. All right, now watch what's going to happen when I add in my not West Coast variable. When I add in my not West Coast variable, it all looks okay, but watch when I go to my multiple regression. See if you notice anything. I'll let you stare at it for just a second. Notice anything here? Should be pretty obvious. Yeah, it can't do it. There's a lot of things that says, I just can't do this. I can't do it. And the reason why is that when we add in this variable, it's now over-determined. And just simply, if I know, for example, that I have a 0 here, I automatically know what this variable is right here where it says not West Coast, right? It's a 1. If this is a 0, this must be a 1, right? So anytime you end up with a situation like that, just take out one of the variables and you should be okay. So if we just take out one of the variables here, for example, there it is. Everything's back in our table, and we're good to go. All right? And so hopefully that makes some sense. The idea that I'm thinking of is in the forms example. In this case, we had a company that they looked at, they're processing something like maybe a loan application or who knows what, right? And they measured processing time, and there were so many fields that were there. And they thought, oh, I can regress that against that. And it turned out that that was not a very, oops, I screwed up. It was not a very strong regression. I'm just going to use nnum here. Okay, I'm not going to use nnum. Let's just use 2num. All right, well, clearly something is going on, and I'm going to close everything up. Hopefully that helped. Close and don't save. Usually the remedy. Okay, and we will do a 2num here. And we got something that wasn't all that helpful. Plus, there's a honking outlier over there. We looked at our R squareds, and where's the R squared? It's just not that strong. It's 49%. So we might want to improve it. And I think what I said was, well, we have, in form type, I just don't have that many types of, or these are the types of forms I've got in there. I've got A, B, C, D, and E. Okay. So if I call this A, and I call this B, and I call this C, and I call this D, and I call this E, and let me do an if this is equal to the label on top. I'll put a $sign there, $sign there. Then my switch is on, otherwise it's off. Let's see if that worked. Oh, there we go. So hopefully this makes some sense what I'm doing here. I'm creating that dummy variable. So this is a B, so that B switch is on and everything else is off. That makes sense. You keep going for a while. Okay, this says it's A is on. There it is. Okay. B, 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 A, C. Yep, there it is. Okay, good. So it looks like this variable works. And we'll just copy that down. And now, if I wanted to do a multiple regression, I'd have to omit one of these. And I think you'll see why in just a second. So I'm going to look at processing time versus the number of fields. And let me eliminate E for just a moment. I'll make that equal to, whoops, I'll just take it out. And you'll see that when I take that out, I can get a model. I may want to take out other things, like A looks like it's not that significant. That's fine. But watch when I add E in there. When I add E, I go back to my multiple regression, and it's all screwy again. Now, this time it didn't give me num, but it gave me all these screwy numbers where I have the lower and upper the same. And why is it doing that? And the answer is, when you get screwy numbers like this, you're probably over-determining it. And if I go into the data, you'll see it. So if I covered up, for example, if I covered up this column B and I hid it, and I didn't tell you this also, and I hid this, I could always determine when I had a B. And it's when all of these are 0. If all of these are 0, that means form B was used, because it wasn't A, it wasn't C, it wasn't D, and it wasn't E. So we really only need 4 of those switches to determine 100% what's going on in the model, so we don't include all of those in. It's really that simple or that complicated, depending on what you thought that explanation was. Okay? So when you're doing indicator variables, you always want to use one less than the total number of possibilities. All right. For multiple regression, that's what or for all the regression, that's basically it. We've got the simple. If we want to make it stronger, best way to do it is multiple regression. If we want to fit curves, polynomials, transformations helps us with this robustness. And then we've got these indicator variables. Okay, enough about that. I want to talk a little bit about DOE. And this is the week 6 stuff, design of experiments. Now, we talked last time about one of the problems with regression. And you see it all the time. Like I read yesterday in the paper, somebody was talking about the stock market always going up with March Madness. Okay? So the question is always, or one of the questions is, well, does X cause Y? So do we really think that, for example, the results of the March Madness tournament caused the stock market to go up? My guess is probably not. It probably has nothing to do with the March Madness per se. It probably has something to do with something else that it's correlated to. So, and the other example that I gave was ice cream sales and the number of drownings. Right? Those two are correlated with each other, but they're probably not causal. Like ice cream sales probably don't cause drownings. So how can we, what happens when we come to a situation we're trying to improve a process? We want cause and effect, right? We want to show that our solutions really make a difference. One way that you can establish that is by using a DOE. So one of the benefits of DOE, let's talk about the benefits first. As we go through this designed experiments, and I'll tell you what it is in just a moment, but one of the advantages is you can establish cause and effect. Okay? That's an absolute key. All right, let me ask you this again, or a different question. Let's suppose you went to the doctor and your knee was hurting. And the doctor said, well, here's what I want you to do. I want you to take this pill that I'm prescribing. I want you to get some bed rest. I want you to stay off the knee for a while, but I also want you to do a specific exercise. So there's 4 different things that the doctor said to do. Let's say you do all of those things for a week. Which one of them worked? you don't know. Maybe were there some things that didn't help at all and other things that were helpful? Maybe even some things were hurtful, but they were offset by the helpfulness of some others. So the question is, do you ever get that feeling when we fix a process, we usually don't just implement one thing. We usually implement a number of different things. Wouldn't it be nice to know which ones were really helping, which ones were not helping, and maybe even by how much? Kind of makes some sense, right? All right, so it can help us. How can I see this? How can I say this? It can help us understand which solutions work. Okay, and the third thing that it can help us with is the following. Let's suppose that you found that let's suppose that you were working on in a call center. You were trying to reduce you were trying to increase the first call resolution. That is the probability that somebody's call will be handled the first time they call as opposed to the second or third time, whatever. Let's suppose that one of the things that you built when you examined this was a new script. And let's suppose that you gave the new script you implemented the new script, and after 2 weeks you noticed that while overall it was a little bit better, there were some people who were doing better and other people who were doing worse. And then you examined it a little bit more closely and you found out that the people who were doing better were very experienced and the people who were doing worse were very inexperienced. What you've identified there is what's called an interaction. In this case, one of the factors, namely script, is interacting with another factor, namely experience level. That sort of thing happens a lot, and knowing those sorts of things is often the difference between something that you can create world-class performance in and something that anybody can do just by sort of brute force. So it helps you understand, helps identify and quantify interactions. Okay, so that's what it does. DOE does all these different things. Do you need a DOE? Now, what are some? I'm just going to say this out front, just so that we don't lose this. I'll say it later. You don't need DOE in every project, okay? But I'm a huge believer that businesses need to experiment a lot more. And once you get comfortable with design of experiments, you'll find that it's extremely efficient and extremely clear. Today, it probably will not be because there's a lot of moving parts, but I'll try and do my best to make it as clear as possible as we're starting out. So let's run through before anything. Let's run through probably the simplest experiment. Okay. Well, actually, let me just ping everybody before I start drawing my stick figures here. Let's suppose that we wanted to know, let's suppose we developed a new drug. I don't know, instead of Lipitor, let's call it, I don't know, Skeletor or something, okay? And it's supposed to reduce cholesterol. Now, none of us are medical researchers, but what would you do? What are some of the things that you would do if you were going to establish that this thing actually did reduce cholesterol?
Can you restate the question?
Sure. What would you do if you were going to design an experiment, if you were going to run an experiment to see if this drug reduced cholesterol? Or what might you do? No, there's no commitment. Go ahead.
Take daily readings?
You could take daily readings. You give somebody a drug and then take daily readings. Mm-hmm. So you could do that. You take some data, right? Namely, you'd measure cholesterol level, and I'm going to write that over here. I'm going to write cholesterol level. You're measuring cholesterol level. What else would you do? Would you do it on just one person?
No, would you randomize it?
You do it on
among a group,
people, right? You do it on many people, right? I heard what you just said. I'm going to take that into account in just a second. So the first thing is you wouldn't just test it on one person, right? You test it on lots of different people, and you wouldn't just give people the drug, right? You'd have to compare it to some people who didn't get the drug. Have you ever heard of doing this? That's called a control group, right? So usually you'd give some people, let's call them group A. I'm going to put something right here called the randomizer, whatever that is, right? But I think we have a idea here. We take some people, we put them into the randomizer, and they either go into group A, right? And I won't draw too many here. Or they go into group B. And maybe group B gets a placebo, and group A gets the drug, right? So then you're measuring the effect of the drug and subtracting out from people who didn't get that drug, right? Now, why do you do that? Why do we do this? Why do we care? Why didn't we just give people the drug and measure its effect?
Because the drug may not work.
Okay, but if it doesn't work, wouldn't the on average be 0? Wouldn't the on average be the population cholesterol level?
Yes.
Yeah. So remember when I drew the ice cream sales? I'll just put IC sales and drownings. Okay. And I said, what's happening here? Remember when we covered this and I asked the question, what's happening here? Are people really being weighed down by the ice cream and sinking to the bottom of the sea? And we said, no, it's probably correlated with something else, right? What would that something else, what might that something else be?
Other factors, they could be on another drug, they could be exercising, they could change their diet.
They could. Now you're back to the drug problem.
Oh,
right?
sorry.
No, that's okay. But in the ice cream one, it's probably, Regina, you and I probably eat ice cream mainly in the summer, right? Because it's hot.
Yes.
So it's also the time when drownings go up. The point is they're correlated with some other type of variable. So what would happen if, for example, some other factors change, like the general state of the economy? Might people feel differently about what they go out and buy in terms of food? We don't know all these things, so what we do to handle that is we create what's called a control group, and the control group helps inoculate us against lurking variables. It's really as simple as that. So it helps us, it's possible that the whole population might have been increasing at that time, and it wasn't really the drug, so therefore we create a control group, and so we can make a comparison over that same time. It turns out that many things are correlated to time. Not just the effects that we're looking at. So that's why you create a control group. It's to avoid lurking variables like this. Let's see if I can eliminate all that. Oh, it's hard to get rid of those dots. Hey, I did it. Okay. All right. So far so good. So we create a placebo, and this we call the control group. Now, if we've done our work okay over here, like if we wanted it to be just if we wanted to have the study just refer to men, then these are all males. If we wanted to be all the population, it'd be women and men, and it'd be maybe different ethnicities and so forth. And we'd randomize them and say who goes in which group. All this making some sense? Hopefully it is. This is sort of a standard sort of experiment. And we're not even getting into blind and double-blind studies or anything like that. But the idea that you have a population, you're repeating measurements. You don't just do it with one. You do it with a number of different people. In our world, that might be I don't just run it through a process one time to see if it works. I might run it through 10 times to see if it works. And then the other thing is I want a control group to be able to compare against to, or a comparison group is another way about this. Okay. The one other thing that you want to probably do is we want to control for noise. So how do we control for noise in a medical study? What are some of the things that we do to control for noise? Well, just for we can also, this also happens, in polls and other things like that. The typical ways that we control for noise are we say, can we run it in an experimental setting? In other words, can we hold some things constant? Like, for example, if we wanted to make sure that people didn't have different diets, we might say, okay, for this you're going to be confined to a certain building. Let's say it's a hospital ward, and we're going to control what diet everybody eats, how many calories, how many vegetables, whatever. That would be one way of doing it. Might be a very expensive way of doing it, but we could do that. So that's one thing that you can do. You can hold things constant, or you can do what's called adding blocking or nuisance variables. Okay, so what are blocking or nuisance variables? We'll come across this in just a second, and then we'll get through the mechanics. So blocking or nuisance variables are, well, we may not be interested in how well the drug works on Mondays versus Tuesdays versus Wednesdays versus Thursdays or whatever, but we know that people have different diets on those days, so I'm going to put that in my experiment, and then I'm going to regress it out. I'm going to take the average of those out so I can look at the results without that. Okay? And we'll see an example of this as we go through our examples when we do a full-fledged experiment. So that's basically, without going too nuts on here, that's how this study might work. We take the population, we put them in the randomizer, randomize them into either the drug or the placebo group, and we call this the treatment versus the control group, and we do measures on these different things. We try and do our best to control for noise, and we do that by running the experiment. We try and hold things constant. We maybe isolate them from outside effect, if we can do it. And if we can't, maybe we take into account some of the variables that are changing by measuring those as well, like Tammy suggested. Like, for example, we're really talking about our main experimental factor is really the drug, but there may be other things like gender that we'll measure. We're not really interested in it, but we'll measure it so that we can subtract out that effect when we're trying to see if the drug actually worked. Okay, let's do an example now, hopefully from our world. I'm going to stop and I'm going to say, what questions do you have at this point about this? So far, so good?
Mark, this is Gina. So what's, I guess, like the definition in the book as far as controlling noise? You have block and nuisance factors, and then you have randomization.
Right.
And the block and nuisance factors, it says you put them into the experiment, and then you adjust
right.
for them in the analysis. And then with randomization, you average it out. So I was just trying to understand, what would the adjustment be then in block and nuisance? Would it be?
So we'll be able to see what that is when we go through the example, okay? And we'll point it out exactly. So when we're calculating the drug's effect, we'll be able to see what gender's effect is also. So it separates out all of the effects as we'll find out, okay? All right. So let's go through a more tactical example, and let's say that you were working on a project, and may as well make this about loan applications, okay? So maybe we're looking at something like the time that it takes to process, the cycle time of loan app. Does it make sense? No? Yes?
Yes.
Okay.
Yep.
Okay, good. So this is our response, we might want to, let's suppose we went through our design, measure, and analyze, and we found that there were a couple of things that we wanted to make changes on. Let's say, and this is a number, right? And this we're going to call eventually our response. Now, we could just go ahead and make those changes, but let's suppose, just for fun, we had 3 possibilities. Let's say we added a job aid to help people do their job better, okay? Let's say we also found out that we could give them different batches. Like we could give them, one day we would, instead of giving them one loan application to work in their queue at a time, and as soon as they finished it, they got another one. Let's say another idea was we give them 100, and we let them work on those 100, and as soon as they finish the 100, then they start again. Those are 2 different ways of processing. And we give them another batch. Okay, so let's just call this batch. Okay, and the third thing I want to put on is number of screens. So let's suppose that we said, I have an idea. We can let them use a second screen instead of just one screen, because then they can look at, scanned files on one screen, and they're looking at maybe their application on another. So let's say the number of screens that are here. All right. So these are what are called. These are what are going to. I'm going to label these as A, B, and C, and we'll see that this notation is pretty common. And it's all arbitrary as to what I put was A and what I called was B, what I called was C. Here's what you might do in the following experiment. Now here we're testing 3 things at once, and what DOE is going to do, what this process is going to do, is if you look at this right here, it's kind of costly to set up separate control groups for all these different things. If you want to test, well, does drug A work, and then I've got another possible solution, right? I've got all these different process solutions. Does that mean I have to form a control group for each one? And the answer is no. You just go through the following mechanics that we're going to go through here. Okay? So you make up a table, and the table might be, I'll call it arbitrarily low and high. And you see how all this works in low and high. And here I'm going to say with the job aid, I'm going to call low, no job aid. And high, using the job aid. Okay? You'll see how this all translates in just a moment. Okay? And batch, I'm going to say single is low and 100 is high. I'll say number of screens, 1 is low and 2 is high. Okay, now notice each of these has only a low and a high variable. I don't have 3, I have 2. And we'll have more to talk about in just a second, but for now, let's just note that. Okay, now I'm going to translate all the lows to -1 and all the highs to +1. Okay, now notice I haven't really done anything except abstract all of these things, right? This is all arbitrary. Low means -1 and high means +1, regardless of what my label for it is. So far, so good? All right, so now what I do is I set up my experiment, and I'm going to write down 8 runs, and you'll see why in just a second. And I want to write down each of the levels that I would have to run, and then I'm going to have to measure the response. So when I set up my experiment, I might have to set up a -1A and a -B and a -C, right? I have to have that, all of those things. If I wanted to check every level of all of the A, B's, and C's, this is what I would have to do. I'd have one that was minus, minus, minus. I'd have one that was plus, minus, minus, right? This represents, the first one represents no job aid, single screen, single batch, and 1 screen. This one represents I am using the job aid, I'm using a single batch, and I'm using 1 screen, and so forth. Okay, so I'm going to keep writing this out. And it turns out that if I alternate these, I'll find that I get it. So minus plus minus, plus plus minus, minus minus plus, plus minus plus, minus plus plus, and plus plus plus. And if you check, you'll find that this contains every single combination of A, B, and C that you could run. Okay? Hopefully this all makes some sense. So all I'm doing is I'm just running each of these factors at each level possible, and then I'm going to measure. Like, so if I assigned, for example, here's my population. Okay? And I randomly assign these guys, right? And I measure every day. I would be able to have, I would have these different responses. Okay? Now, there's a couple of different ways I could do this. I could either randomize people, or I could randomize the bucket that the loan comes in. Okay, I could do either one of those. I could either set up the groups, or I could simply say, okay, for this particular loan application, here's what we're going to use. Here's what you're going to use. Okay, so you could do either of those. Let's suppose that we ran the experiment, and we got the following values for the response, or for the average responses. 27, 37, 27, 34, 36, 38, 34, 34, and 38. So I get different values. Now the question is, what can I say about the amounts of each of these effects? Which one's working and by how much? Or any of them working? Okay, so let's go ahead and do this. I'm going to do this in Excel so that we see sort of how all the working parts work, and only then will I go into a DOE helper, and I'll show you how it all works in DOE helper. But let's do this by hand once. I'm going to stop here for a
Mark,
few minutes. There's a question.
Can I ask a quick question? This is Tammy.
Yes, hey Tammy.
The 1 through 8,
Yep.
ABC without the response, let's say you haven't filled in the response column yet.
Right. Mm-hmm.
Those will always be the same minus, 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 plus, minus, because of you're always converting to the lows to minus ones and the highs to plus one, right?
Correct.
Those are essentially never going to change.
Right. So when we get through all of this, all I'm saying is, hey, if I have three of these guys, I can represent all of them by doing this.
Okay.
Yep. And it's always going to be the same design matrix, as we'll find out.
Okay. Just wanted to make sure. Thanks.
Right. Now the question that we didn't ask, and you didn't ask, is why did I use 8? Why couldn't I use a different one? Well, in this one, I know for how many factors do I have? I have 3 factors, right? A, B, and C, and each one of them has 2 levels, a low and a high. And so if I take 2 to the 3, that equals 8. I know that I can represent it all in 8. And that's why they're called 2 to the k DOEs. But anyway, that's getting a little off, a little bit off target. So let me go into, let me see if I can get into, I want to close down much of Excel. But let me see if I can get into this, and let me see if I can get into the example so I can do it directly in Excel. Okay. So let us see, DOE intro, let's hope it's in here. It appears to be. Hey, look at that. So it's not exactly what I had before, but it looks like it's pretty close. And it looks like I've got my runs all mixed up. So, or do I? No, it looks like I don't. So I have these as the same, right? Minus, plus, minus, plus, minus, plus, minus, plus, minus, minus, plus, plus, minus, minus, plus, plus, etc. Okay. So all that makes sense. And I just have a label on the first one. Let's not worry about that label. Okay, so here's the first question. If I'm going to make a model, and the model is going to look like the following. Come on, Mark. Our model is going to look like the following. I'll have my response. I'm going to call my response y, just like I did before, and it's going to equal some mean, some overall mean, plus a times some effect of a. I'll write down that effect of a as alpha, plus b times some effect of b. I'm going to write that as beta, plus c times some effect of c, which I'll call gamma. Okay? So far, does that make sense? Hopefully it does. However, I might also have part of my model in the interaction term. So I might also have an AB term, a AC term, and a BC term. And I also have an ABC term, an interaction between all three. Okay, so there's some other factor in front of that, right? We'll call this, I'm running out of numbers here, so I'll call this little a, little b, little c, and I'll call this little d. Those are all just numbers, all of these. So how do I calculate these effects that I see in here? All right, so let's go through this by hand, and I think you'll see it looks hairy, but it's actually really straightforward. So let's go ahead and do that. So I said the first thing I want to do is calculate the mean effect. How might you calculate the mean effect? Pretty straightforward. The mean is simply equal to the average of all of the experimental runs. Hello. Okay. So my average is, I'll maybe just put one decimal point. It's about 34. Now how about the effect of A? Well, the effect of A is equal to the average response at +1 of A minus the average response of -1. So notice I don't have to separate out all of these. I'm getting, in fact, 4 data points to be able to average the effect of, 8 data points to be able to average the effect of A. So that's actually pretty strong. So anyway, hopefully you'll see what this is just a moment. I'm going to blow this up so that we can see it. So this is equal to all the average at the pluses. Let's just average these all up. So it's this plus this plus this plus this. Those are all the positive A's minus this plus this plus this plus this. Okay, and we just want to average that. One way of doing that would be to look at the difference of the averages, but let's just divide that whole thing by 4 because we have 4 data points. Oops, hello. There we go. And this is what we'll say is the effect of A. So that's the effect of going from a minus to a plus. So this would be the effect of the difference between having a job aid and not having a job aid. Looks like it's 6, whatever 6 is. Maybe it's 6 hours. Or something like that, okay? So hopefully that made sense. I just take the pluses and I subtract off the minuses. I'm going to do the same thing for B. So the effect of B would be equal to, and now I'm going to just average these. Average all the pluses, okay, and, oops, and subtract all the, come on now, all the minuses. Okay, so B's effect is less. Excuse me. The effect of the batch size is far less than it is on than the effect on of using the job aid. So the job aid is actually more helpful than is the than is the batch size reduction or whatever. Let's now go into factor C, and again, this is just equal to the average of all the highs minus the average of all the lows and there you go. And in fact, C has a small but a little bit of a negative effect. So this essentially says, and by the way, I just made this up, right? This isn't real data. This essentially says that the screen, if we go back to our thing right here, this says that the screen is actually a little bit better using one screen than two screens. So this allows us to understand all of those things that are put in, the amounts that they're put in, and so forth. So now when we're building our model, we can say that, well, this is the amount that we get because of the job aid, this is the amount that we get because of the batching, and this is the amount that we get because of using one versus two screens. So we actually can separate out the value of each of those things. I want to show you, so I'm going to pause here for just a moment and answer any questions you might have. So this hopefully should also take into account, remember when we did the doctor when you go in with your knee and the knee's got all those problems and he gave you 4 solutions? If you ran experiments, this would be, I'm not saying that we want the doctor to experiment on your knee, but if we were running experiments, the doctor would be able to know essentially how likely it was, how much bump each one of those things was giving, the rest and being off it and giving you these pills and so forth. We'd be able to separate out all their effects. Now I want to show you one more thing, and that is the interaction. So let's just do one more interaction. And this is how we think about calculating. It'll turn out we do not have to do this, but this is how we think about calculating the interaction. If we were going to think about it by hand, let's calculate the AB interaction. Now, AB, there really is no AB variable, right? There's A, there's B, there's C, but there's no AB. We can think of this interaction as A times B, okay? And to do this, we literally take A and B and multiply them together to get a new column. So if we did that, for example, A times B minus 1 times minus 1 will give me plus 1. In fact, I'm just going to do that. This times this. And that gives me, and we'll check it, minus minus is a plus. Plus minus should give me a minus. Let's see if it does. It does. And etc. Okay? Now, if you check into this, you'll find that this is a unique column. It doesn't match any of these others. But we can calculate the AB response, A times B interaction term, exactly as we did before. It's the average of the plus ones minus the average of the minus ones. So it's the average of all the plus ones. Oops. Come on, see if I can get that right. Keep doing the under. There we go. Minus the average of all the minus ones. Okay, so it does turn out that the AB interaction is 2. Whatever that is, that means that we need to take into account how A and B work in this case, they work in concert. If the interaction is positive, they work in concert. Sometimes they work opposite to each other, in which case you'll get a minus. And that means if you're going to adjust A and B and try and optimize, you've always got to think about how they both interact together as opposed to one. Now, how does this translate? Now, we're not going to do the rest of them. I'm going to use DOE Helper to show you how that works. But how would this translate into the model, that y equals whatever that we had before? Well, here's how it translates into it. We would have a model that was, we would essentially get the following model. Y equals 33.9 plus 6.75 times A. Remember, A can be either minus 1 or it can be plus 1, plus 3.75 times B minus 0.75 times C plus 2 times A, B. Okay? So for example, and there's more here that we would have more in the model, but we can just stop here for just a second. For example, if we had, going back to our screen right here, if we had no job aid, let's say we had the following. Let's say we had no job aid, single screen, and excuse me, and no, I'm sorry, single batch and 2 screens. What would that be in terms of our answer? What would our model tell us? Well, it would be y equals, let's see, A at the no job aid is a minus 1. So this would be equal 33.9 minus 6.75. We had the B at the low level, at the low level, right? It's single batch, so that's minus 3.75. We had C, on the other hand, using 2 screens, so that would, C would be a plus 1, so that would subtract 7.5 for us. And A times B is plus 1, right? Because minus 1 times minus 1 is plus 1. So we add plus 2, and we can add that up, whatever that is. So 33.9 minus 6.75 minus 3.75 minus 0.75 plus 2. That's our answer for the response that we would expect if we had all those settings in place. Okay? So I'm going to pause here, and I'm going to ask, what questions do you have? And then we'll do this we'll do the whole thing soup to nuts in DOE Helper, and you'll see it's really not all that bad. And then we'll do a few more examples, and hopefully we'll nail it. Okay. Okay. So let me address, before I do that, let me address Gina's question, which was, hey, what happens, what if we have a nuisance variable? Here's how a nuisance variable works. Basically, a nuisance variable, what might be a nuisance variable over here? What might be something that causes noise in the loan application process? How about experience level of the whoops. How about experience level of the processor? Experience level. Okay? Now, why do I say that's a noise factor? Well, I'm probably not going to say, hey, you know what's an improvement to my process? I'm going to make everybody experienced. That's not a viable solution. So it's really a nuisance variable. I'm not crafting it in the experiment as a solution. However, it could cause a lot of noise in my experiment. Does that make sense? I'm hoping that makes sense. I didn't get a response, but I'm hoping that makes sense. So essentially what I would do is I simply add it as factor D, and it would get its own column. And you'll see how this works out in just a moment, okay? I promise. You'll see how this works out today. However, we would just then do the calculation exactly as we did here. So it would go into the model. If it turned out it was significant, then we would keep it. If not, we would not worry about it in the model. Okay? Now, generally speaking, I didn't talk about this, but when we looked at our model, oh, come on. When we looked at our model, this guy right here, which one of these effects is more? Which one of these effects? Which of these effects are most important?
A and AB interaction.
Good. So A is definitely A is definitely the most important. The short answer is whatever is the bigger number, okay? So A is definitely important. B is definitely important. AB is a little less important. C, I may not even include that in my model. I'm going to give you just like we had with control charts, I'm going to give you a cut and dried rule about how do I include it in my model or not. But just right now, just from a practical point of view, the ones that are big are important. The ones that are not that big are not important. They're probably just noise. Okay? So that's what we're going to do. All right. So let's go ahead and do this in DOE Helper. And I'm going to get rid of this column F right here because we don't really actually do that in DOE Helper. All right, so let's open up DOE Helper. And this should be exactly the same one that you have on there. And this is a Buyer Beware. It was written by me back in 2005. So you can see that there's various things of 4 trials, 16 trials, 8 trials, 32 trials. We did 8. And you see right here it has, factor A is -1 plus 1, just as Tammy said, -1 plus 1, -1 plus 1. Factor B is minus plus plus. Factor C is, okay, good. So it's all there. And we don't have to do anything with this. We don't have to do anything with anything. We just have to paste in the response. That's all we have to do. Now there's some other bells and whistles over here. We're not ready to interpret these yet, so just hold on to your horses, okay? Right. We see these things that say effects and all this kind of stuff. Okay, so let me put this in. I'm going to put in a response because it matches this. That's the main thing. You want to make sure that this matches, which it does. So I'm going to paste in the response. And voila. That's it. And let me see. I'm going to run the 8-trial analysis. And these numbers should look, it looks like I messed up a little bit to do it looks like I got a negative sign in there somehow. I know why I got a negative sign, because this is absolute. But the coefficients are negative. I'll tell you what the coefficients are in just a second. So, I messed up a little bit. But essentially here, you should recognize these effects right there as what we did before. There's I must have messed up for the AB interaction a little bit. But in any event, there's my 6.75. There's my 3.75. And down here, it tells me what my model is. Now, what happened to some of these things? And what is D? Well, I'll tell you. What happened to C was that C was too small, so it got taken out of the model. These are the effects that you see right here, and the ones that are red are the ones that are significant and stay in the model. Okay, so far that should make sense, except for D. What the heck is D? D happens to be an interaction, and it's the AB interaction. Now, how do I know that? Here's how I know that. I can come over to here, and I can see it says 2-factor interactions, and it says AB is equal to CG is equal to EF. Well, A and B, I certainly have both A and B in my model. This next one says CG. Well, I have a C, but I don't have a G, so that doesn't exist. That interaction cannot exist, so it can't be CG. And then EF, I don't have an E or an F, so it can't be EF. So these are the 3 things that I have. A, B, and D. I'll mark those. And this one must be the AB interaction. Let's make it bold. There, you see it right there. Okay, so it must be the AB interaction. All right, so if that was a little bit difficult, and I understand it was because we had this interaction, basically...
Can you explain to me one more time why you can have a D when there is no E and F?
Right. So, oh, why I can have a D. So it's not really D. It's really AB. Okay? I really only have everything up to
First three, right?
I really only have these first three. I really don't have these. So these don't exist. But it's coming up as something that, oh, there's an interaction term that's right here. It says D. I know there's no D in my model, so it must be an interaction. That's the way you think about it. Okay?
Okay.
So there's always going to be 7 things right here. When I have a factor of, or when I'm looking at 8 runs, I'm always going to have 7 things that I can estimate. So I could have put, if I wanted to, I could have put, instead of just looking at A, B, C, I could have looked at factor D and E and F and G. It would have hurt me, but more on that a little bit later. Okay, let's go through the whole thing soup to nuts with another pretty simple example. And this one I want to do in the book, and then we'll do a couple of more complex examples. And I think that'll be enough to kind of get what's going on. Okay. So I'm going to close DOE Helper because I've altered it. The example that I want to do is the example that is in our PowerPoint starting on slide 22. So I'll just go to it. And this is on the yield sheet, so we'll actually be able to do this in DOE Helper. So this one maybe at a chemical process or a chemical plant or something like that, certainly maybe more applicable to the folks from Amatec who are in here. So suppose we want to improve yield. That's an output of a response of a chemical process, and we've got 3 key factors. They're identified by subject matter experts, SMEs. So we've got temperature, which is factor A, concentration, factor B, and catalyst, whether I add in additional chemical that's going to help it make the reaction go faster. So I know we don't all understand the chemicals, but this should be analogous to what we did before. The first thing we want to do is we want to set the levels of the experiment. Now remember, we can only have 2 for each one, a -1 and a +1. So for these, for example, temperature, there may be many different temperatures. So here's the basic guidelines. You pick 2 extreme but not super extreme values. So for example, in this process, temperature might reasonably be between 160 and 180. You'd pick those as your -1 and +1. Okay? For catalyst, on the other hand, if you had a choice of, say, 4 or 5 catalysts, you might pick my -1 is going to be my worst, what I think will be my worst catalyst. My +1 might be my best catalyst. Let me make this into the example that we just did for a second, because I think it may be helpful. Well, I hope it is. So another one that we might have used instead of experience level might be as a nuisance variable. We can add both nuisance variables, by the way, but what if we use day of week? Like, you know how some days people just work better than others? Well, maybe I would pick what might be my worst day, which might be Monday, and I'd pick that as my -1, and maybe my best day, which might be, I'm making this up, might be Wednesday, and I pick that as my +1. Okay? Now, you have to use some care on this, and if you want to use multiples, you could use another variable in there. But that's essentially how you might set that level. Okay, back to the regularly scheduled thing. This is usually easier than it seems. Okay, so there it is right there. We've picked our lows and highs, and we translate those into -1s and +1s. And that's arbitrary. Okay, then we plug into our 8 trials. How do I know that it's 8 trials? Well, because I have 3 factors, and 2 to the 3rd power is 8, and that's going to give me every combination of these. And I can either write them this way, or I can write them this way. Those are both equivalent, this design matrix or this. In order to use DOE Helper, you have to write it like this, with -1s and +1s. Okay? Once we do that, we actually run the experiment. Now, I'm going to have one more step in here that I didn't talk about, and that's randomization. I really should randomize the order that I do this. That would be sort of the normal industrial experimentation, where I randomize the order. But like we said before, you can actually, instead of randomizing the order, you could randomize the people that were assigned to do different tasks or different settings. Either one's possible. You can randomize it, though. Then we run the experiment. That's it. To run the experiment, you have to prepare people. You tell them, what forms you're going to use, because you're collecting data. Just again, as Tammy said, we're going to collect it daily or weekly or whatever is the answer to that. And suppose we got these results. So let's go ahead to analyze this, and we'll be able to flip back here to see if we got the same results. Okay? So it looks like my original was a minus, plus, minus, plus, minus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, 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 plus, 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 plus. That matches what we have in DOE Helper, thankfully. So I just need my my yield organized in that way. So let's go ahead and do that. It's on the yield. Okay, so it looks like let me blow this up a little bit so we see it better. It looks like I have my minus, plus, minus, plus, minus, 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 plus, plus, and so forth. So this looks like it's the right order. All I have to do then is copy this and put this response into DOE Helper. So let me open up DOE Helper. Go to 8 trials. I'm going to plop my response right in there, and then I'm going to click the Run the Analysis. And voila, there it is right there. It says A, B, and E are important. So let's see if we can interpret this. A then is, it looks like factor A, which is temperature, is important. Okay? And it looks like B is also important, which is concentration. And catalyst turned out not to be important. Right? That's C. Okay, and then what about E? What is factor E? Let's see if we can walk through this. So what is factor E?
Your AC interaction.
Excellent. So that is correct. So Gina, how did you come up with that?
So on your DOE Helper under factor and E,
Yep.
the 3 options that are available, we only have the first, which is AC.
Excellent. So AC is the only one that's available, so that works. Now there's one other thing to think about as we do this. Excellent. So that's basically it. We're ready to use this model. We can plug in numbers now and say, well, what happens if we had it at the high temperature, we used the, excuse me, what was the second? The high concentration, and we used the cheap catalyst. What's the response that we would expect to get? And it tells us. I mean, very, very powerful. We could choose to, there's all sorts of things that we can choose now. We can choose, well, we don't want to use the cheaper catalyst, or we don't want to go with the expensive catalyst because it really doesn't get us all that much. So that can be taken off the table. But on the other hand, with the temperature, we just have to make sure for sure that we have the right temperature, whatever, if it's the high temperature or whatever, when we do this response. So we also, whenever we have an interaction, we should stop and we should think, is one of the, at least one, and usually 2, but is at least one of the other factors that's in that significant? Now in this case we didn't have to worry about it because B, G, and D, F didn't even exist, but sometimes when we get into this a little bit later, we're going to find out that there are some things that exist there, and we're going to have to make some tough decisions on this. Okay? So I'm going to pause right here for just a moment, and I'm going to talk about what is some of the notation, what is some of the language that we what's some of the language that we've been using? So first of all, we've been talking about outputs, and instead of calling them y, we've been talking about them as the response. That's just part of DOE. We call those response. We talk about the factors. By the way, we usually use A, B, C, D. Why, I'm not sure, but we do, instead of x1, x2, x3, x4. But they're basically exactly what it is. These are called the factors. Okay? And the minuses and pluses that they take on, minus and pluses, those are called levels. Okay? So we can talk about, what's the high and low level, which factors are in the model, and so forth. Okay, so I think that's enough of the terminology to get us dangerous. So far so good. So I advertised that DOE was really efficient. Let's before we do any more examples, let's see if it is. What if I had 3 factors? How many experimental runs would I need to make? Well, it's 2 to the 3, so that means I would have how many experimental runs?
8.
8. Okay, how about 4 factors? That's 2 to the 4. That's 16. We'll do a couple more. How about 5 factors?
32.
32. How about 7 factors?
I'm going to need a calculator.
It's 128. Okay, but Mark, I thought you said that this was efficient. This does not look efficient to me. Now I'm having to run all these experimental things. Why is that? Well, the beauty and also the difficulty of this, and we'll see how it works out in practice, it's not all that difficult, but the beauty of this is that, generally speaking, remember when I wrote out all the interactions, like with 3 factors, I had ABC, I had AB, I had AC, and I had BC, and then I had ABC, and I also had a mean. This was no accident. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 trials. So in 8 trials, I can estimate 8 things. I can estimate the mean, A, B, the main effects, A, B, and C. These are called main effects, by the way. Main effects. I can do the 2-factor interactions. And I have a 3-factor interaction. Okay? Now, for all practical purposes, what we care about is we care about the mean, we care about the main effects, and we care about the 2-factor interactions. We don't care about things that are more than 2-factor interactions. This is highly substantiated by 2 different things. One is it almost always gets lost in the wash. So there's a guy named George Box, and that's really true. George Box, who invented the Box-Cox transformation, among many other things. Believe it or not, he did not invent the box plot, but oh well, that was John Tukey. In any event, he called something sparsity of effects, and that simply means that as you increase the interactions, the effects of these things get lesser and lesser. So what we can usually get away with is, for example, let me write the whole table out, and then you'll see what's going on, I think. For 16 trials, if we have the 4 factors, we have the mean mu, we have A, B, C, D. Bear with me here. We have AB, AC, AD, BC, BD, CD. A lot of interactions there. Oh, God. We have ABC, ABD, ACD, BCD. Did I miss one? I missed one. Somewhere I missed one. ABD. I missed one. And then we have A, B, C, D. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oops, I've got one extra. I don't know how that happened. I must have counted wrong. But anyway, there should be 16 of them here. Let's see, 5, 6, 12, 13, 14, 15. Yeah, okay, that works. Something's wrong here. There should be 5, 5, 4, 5, 5, 4, 1, 1. Okay, yeah, 5, 5, 4, 1, 1. I got an extra one here somewhere. Must have a repeat. I am not going to dwell on it. Okay, in any way, that's a Mark Zabel error. There's 16 of them. Most of these I could care less about. All of these things I'm not that worried about. So I can get away with doing a smaller experiment. Or I can use 16 trials and get more main effects in. So the beauty is that we're going to find out that we're going to be pretty comfortable using 16 trials. We can go all the way up to about 5 or 6 factors. That's pretty amazing. So you should be sitting there saying, you mean I can study 5 or 6 things with only 16 runs? And the answer is yes, because of this sparsity of effects. So, so let's see how that works. I'm just going to show you in the slides how that works, and then I want to do an example, and then we'll have to cover, I'll stick around and afterward to answer any questions you have, but I want to cover an example or two so that you see how it works. It's not actually that bad once you get into DOE Helper, but I want to substantiate why this is so. It's called fractional factor. And by the way, if you missed any of the how to calculate it by hand, it's all in here, as well as analyzing a Minitab, which we don't use. Okay. All right. So we use this fractional factorial. So here's why we need to do it. The reason why we need to do a fractional factorial is some of the when we get into this, when we add some other, let's take it simple. Let's suppose we had 3 factors and we had only 4 runs. We know that this isn't enough. We know we should have 8. But let's say we only had 4 runs and we wanted to calculate everything. Why is this so that it's actually equal to various things? We call this being aliased. Well, let's create the BC interaction. When we create the BC interaction, we find that it's exactly the same as column A. And that means that we won't be able to tell the difference between A and BC. Now that's bad because those are interactions that we care about. So it turns out if we choose our experiments judiciously, and I'm going to show you how to judiciously do them. It's actually really simple. You just look at a table, and if it's green, you're good. And if it's red, you're bad. But if we choose these judiciously, we can make sure that we never have this happen where we set all of these things down to the 3-factor interactions that things are confounded with. Okay? And that's called resolution. But let's not worry about that for a second. Let's just walk through an example, and you'll see how resolution all works. So to do this, I want to do the example that is on, I think it's all way in the back. There's lots of examples that are in the middle, or there's an example going through every gory detail, but I want to do the exercise. Let's do the bicycle exercise. That's on page 63. Okay, so in this case, the data that's in bicycle.doe come from an experiment to determine what's the best configuration for climbing a hill on a bicycle, and this I actually did. So there's 7 factors. There's the seat. There's whether or not you have the dynamo for the light. I don't know if you know, on some of these 10 speeds, they have a little dynamo that you can put on to have lights in the night. So whether you have that dynamo on or off. There's the handlebar position. There's upright or down. There's which gear I had it in. Do I have it in a high gear or a low gear? I think we can see what's going to be significant. There's whether I had a raincoat on or not, because sometimes it rains and maybe I take longer in the rain. That's a noise variable, right? That's a nuisance one. And there's breakfast, and whether I eat breakfast or not. And there's tires. Do I use my smooth or knobby tires to climb up this hill? So I have, in this case, let me shut down DOE Helper. I'll open it back in just a moment. I'll shut down this. But I want to write just the background here. Here I have my climb time, and I have 7 factors. A, B, C, D, E, F, and G. Okay, whatever those were. Okay, I have to set the highs and the lows. Maybe for gear, I might have first gear be my low, and 5th gear be my high, etc. Breakfast, I might say my low might be I didn't eat breakfast. My high might be I did. So let's just see how this all panned out and how it all worked. So how did I choose 16 runs? I think that's the first important question. So let me just show you how I chose 16 runs. Okay? So on this thing that says check resolution, and when you read the book, you'll find that this is what resolution really says. A high resolution is good. That means that I can tell the difference between first and second order effects. A low resolution is bad. So if I click on this, I look over here and I say, hey, I have 7 factors. I want to choose the lowest number of runs that's at least yellow. You can look down here. 8 would be bad. That says it's resolution 3. Don't worry about what resolution 3 means right now. It essentially just means it's bad. 16 runs is resolution 4, and so is 32. So I should probably pick 16 because it's going to be cheaper to run 16 than to run 32. Hopefully that makes sense. So I use this little chart to determine what my resolution is going to be. And so now I go to my 16 trial runs, and I'm going to check to make sure that I can plop in the response. I actually ran my experiment. It's called bicycle. Here's my bicycle, and it looks like, okay, those are my, seat, minus plus, minus plus, minus minus, plus plus. Now I really should check to make sure all of these match, but I'm not going to do that. I'm just going to copy this and put it in to my response and run my analysis, and there it is. It says B and F are significant, and are B and F in the model? I mean, are B and F in my experiment? Let me see.
Yes.
They are, right? Because in this case, I have 7 factors. So this is, if I go A, B, well, I guess I've got it lined up. So dynamo is B, that's significant. And F is significant. Breakfast, that's interesting. Or was it D?
No, it was F.
Okay, it was F. Now that's interesting. I think I tried to set this up so that it would be D, but which was the gear. This says whether I ate breakfast or not was the really significant thing, which doesn't ring true. But in any event, that's what the experimental run gives me. So so that's that. There's no interaction, so I don't have to worry about anything goofy. So let me do the, so hopefully that makes some sense. Let me go back to, I'll close that up, and let's do the insurance one, or advertising DOE. That is on the next page. So in this one, we've got a marketing department that ran a design experiment to test the effectiveness of their ads. For each one of the they did 16 trials. But before we know that, we've got 1, color, placement of ad, free offer, day posted, and font. So they've got, they've got 5 factors. And if I go into my DOE helper before I do anything, I have 5 factors. I want to check the resolution to see how many experiments I should run. So if I have 5 factors, what would you suggest? What experimental run would you suggest? How many trials would you suggest running? 5 factors.
Since there's no yellow, would you go to 16?
Yeah, so there's no yellow, so green is even better if we can do that. So why don't we do that? Like, for example, if you had 6 factors, you would have some justification to go to green if you wanted to know more and more. That would help you understand, like, really deeply 3-factor interactions. I'm going to show you what might be some of the issues with this, but let's go through this one. Oh, actually, this one's going to be really good. So we should use 16, and that's in fact what was run in this experiment. Okay? So this was the experiment that was run. So again, we should check to make sure that this is exactly the same as in DOE helper. I'm not going to do that right now. I'm going to just copy it, and I'm going to paste it into the 16 trials and run my analysis. Click on that. And there it is. It says B, C, and N are significant. So somebody help me interpret that. So just a second. I'm going to come back here. I've got A is color, B is placement, C is free offer, D is day, E is font. So it turns out B and C are significant, and as well as N. So my model has what factors in it?
I have B and C, but then when you look at N, it could be A and E or B and C.
Excellent. So in this case, right, so this is what I wanted to point out. So in this case, unlike the other, we've got 2 2-factor interactions that are significant inside there, or that could be significant. It could be AE, or it could be BC. So, Mike, which one would you guess it is?
BC.
BC, and why did you say that? Good answer.
By themselves, they're statistically significant.
Exactly. So along with the whole sparsity of effects, there's also something called the Heredity Principle. And this was established very well by a friend of mine, actually. His name's Mike Hamada. He's at Los Alamos National Labs. And basically it states that if you have an interaction that's significant, generally speaking, almost all the time, you'll have at least one factor is also significant. So in this case, we've got both B and C significant, and we've got N significant. So N is probably so we're going to go with N as the BC interaction. So our model is going to be and I'll just kind of put these in yellow, it'll be our constant term plus our value for B, plus our value for C. I'm saying it a lot today. Plus our value for N, but the N is really the BC interaction. So we've taken a fairly complex situation, we've reduced it down to a simple model, but it's actually probably more insightful than a lot of the complicated models were before, because now we know that essentially the placement of ad is important and the free offer is important. We can go into figuring out what is the best what's the best settings for all of these by taking into account all 3 of those things: the placement of the ad, the free offer, and the interaction between those 2, to make sure that we place when we make the free offer, we place that free offer in the right place to get the most bang for the buck. That's basically it. Hopefully you get the mechanics of this. That's the most important thing the first couple times through, is to say, okay, I've got the mechanics down, and because as you say, there's a lot of moving parts, or as I said before, there's a lot of moving parts. So the process is, number 1, decide you want one, decide you want a DOE. Not every experiment needs it. We'll have a recap maybe next week on this, but there's plenty of reasons why you might want to have a DOE. Establish cause and effect. I want to be able to understand interactions. I want to measure how much of an effect each one has. All sorts of reasons. Number 2, decide which factors. Which factors. And you want to have at least some control factors. Control factor would be like your job aid, and possibly some noise factors. Noise factors help you control noise. So this might be the job aid in our example, and this might be the experience level or day of week. Let's put day of week. That's a nice noise factor. Okay, because I mean, do we really care about what day of the week it is to help our process performance? I'd love to be able to take that out. Okay, once we know we have our number of factors, then we decide how many runs. Number of runs. And remember I said green or yellow. This turns out to be at least, in our book, at least res 4. But we didn't talk about that today, so don't worry about that. You're just going to look on that chart and go, is it green or yellow? Then we run the experiment. That's actually the hardest part. We haven't even looked at it. We analyze it. And this is just looking at which terms significant, including interactions. And then we can plug in values to make predictions or to optimize. Let's call it optimize. This is true optimization because we're picking really optimal settings to get the most out of our experiment. So that's a recap. Next week we'll talk a little bit about, or next week, on Friday we'll talk a little bit about this and recap it. We'll do maybe 1 or 2 more examples. Please try the homework, or at least one of the DOE questions, to see if you can get it or not. And if you can't, then you'll have time to ask the questions. All right, that's it for me today, gang. I know there was a lot today. I'm going to end the recording. But I'm going to stay on the line for a little bit if you do have any questions. Thanks for your time today. We'll see you on Friday.